Okay, I want to do a brief presentation on sums of geometric series as we saw in Chapter 2. So there is an appendix on this in the book, and I think it's solid, but sometimes it helps to kind of just go through the process live rather than as a wall of text to make better sense of it. And so that's what I want to do in this example. So it won't cover everything that's in the text, but hopefully it kind of gets your wheels on the track and allows you to navigate the text a little bit easier. Okay, so like I said, we're going to talk about sums of geometric series, but before we do that, we need to understand what geometric series are. So this is an example of a geometric series, 1, 2, 4, 8, 6, and certainly you sense a pattern. And one way that we could express that pattern is writing two successive powers, in integers, 2 to the 0, 2 to the 1, 2 to the 2, and so on. Okay. Now, more generally, we might write this like this. Okay. So a times r to the power, where the power is starting at q and increasing by 1 at each step. And we can continue to generalize this like this, where we start at where the step size is epsilon, and then we increase by numbers of epsilon, right? So in the example, we were increasing by 1 in the exponent, but we could increase by any solid integer, and we would call the size of that integer, or not even an integer, just an interval, I should say, and we would call that fixed interval epsilon. Okay. So we could even generalize beyond this, and I do in the text, but that's good enough for right now. So if we're looking at any one of these terms, it might look like this, where in the, right, so we have a to the r to the q plus I to the epsilon, where I is meant to represent 0, 1, 2, 3, etc., and we can index over that. And so when we look at our series that we looked at the concrete one, then it would be a equals 1, r equals 2, q is 0, and then I to the epsilon is I1. Okay, or I shouldn't say I to the epsilon, I times epsilon. Now, more generally, when we're looking at MaxEnt stuff, where we're looking at exponentials, these values will be different, right? So r will be often e. A will be some indexable number, like it might be y, or it might be I. Okay, so we're just generalizing that. I'm sorry if that's a little bit confusing, but hopefully the text also clears it up in conjunction with this. But for our example, we're just going to set a equal to 1 anyway. So, anyway, this might be what our geometric series look like in or a term in our geometric series looks like in MaxEnt, right, where we're working with these exponentials. Okay, and so if we set a equals to 1, then that expression right there becomes e to the negative lambda y. Okay, and that should be familiar as one of the terms in the series that we looked at in Chapter 2. Okay, so a series then may look like this: e to the 0, e to the negative lambda, e to the negative 2 lambda, and so on and so forth. Okay. And then one more thing notationally, especially I'm pointing this out because I do this in the text to simplify some of the notation there, but we might call this quantity here e to the negative lambda, but more generally r to the epsilon as being capital R. Okay. So now that we know what a geometric series is, we can talk about taking the sum of a geometric series. Okay, so let's call the sum S. And so now instead of separating each term there with a comma, we are adding them together. Okay, that's what it is to take a sum. And so the question is, how do we go about finding this sum? And there is a nice trick. There's a nice trick for this. There's other ways to derive this with calculus and stuff, but this trick is so intuitive, it's hard to resist thinking about it in these terms. So we define another term called RS, where remember we just talked about the term R being equal to, in this, well, being generally equal to little r to the epsilon, but in our case it's e to the negative lambda. Okay. So we define that. So each term that was in S, we just simply add an e to the negative lambda in front of it. Well, each time you do that, when you have like bases, here are like bases e, and you multiply them, well, now you can just add the exponents. So that term, I'm sorry, that expression simplifies to this expression. Okay, so e to the negative lambda, e to the negative 2 lambda, so on and so forth. Okay. This is still part of the trick now. Now we subtract we subtract rs from s. Okay, so we just take the expressions that we've already, I hate to say derive, we haven't really, we just, clarified them. Okay, and we subtract rs from r. And when you do that, all of these terms cancel except for the two bookends. Okay, so it turns out that s minus rs is, in this case, it's the first term minus the last term, and here the first term is e to the 0, and the last term is negative e to the negative n lambda, where n is the peak of our, or the top of our sums, or the highest term in our series here. Okay, so s to the rs, we can simplify that in a few ways. So over on the left-hand side there, we've just simply taken s out of that expression. Now we call it s times 1 minus r. And then we just combine the remaining terms from the sum that we found, e to the 0 minus e to the negative m, or n lambda, and e to the 0 is 1. So now we're at s times 1 minus r equals 1 minus e to the negative n lambda. My computer is not responding to my mouse clicks. There we go. Okay. So now if we just simply divide 1 minus r over, now we finally get the sum for s. Okay. I guess I won't read it out for you, but that is what the sum is. That is what s equals. Okay. So we've just gone through an example with exponentials here. And you can apply this process basically to any sum of geometric series. Now, one more addendum here. So what we've done here is technically sum of a finite series, right? We had a finite number of terms in our geometric series. But we could also do this for infinite series. And so when we do this for infinite series, now our s and rs terms, they just simply go on forever. There is no termination to them, right? And so now the only term that we're left with is the e to the 0, and that e to the 0 then just equals 1. Okay, so now s times 1 minus r equals 1. Okay. And so that means then that when we divide over 1 minus r, we get 1 over 1 minus r, or in this case, 1 over 1 minus e to the negative lambda. Okay, so again, hopefully in conjunction with the text, that provides you a solid handle on geometric sums, or sums of geometric series.